Good afternoon, everyone. I hope my slides are visible to you all. And my voice is audible to you all, right? Okay, let us start the seventh tutorial of this course, Introductory Organic Chemistry 2, which is conducted by NPTEL and whose course instructors are Professor Harinath Chakrapani and Professor Neeraja Dashaputre from ISER Pune. I'm Deepika, your PMRF teaching assistant. I'm doing my PhD in chemistry at IIT Bombay. And on today's tutorial, we are going to cover the topics conjugate additions to carbonyls, and also we are going to solve extending the topic of various condensation reactions. We are going to we are going to study a few more mechanisms related to the topic of condensation chemistry, and most of the topics related to this particular field we have already covered in two of our last tutorials, and the recordings of those tutorials you will get in the YouTube channel also, which is Tutorials by Deepika. The recordings are available there, you can go through those. So let us move to today's tutorial. So let's start with this easy question: which of the following predominantly gives the carbonyl addition product of pen 3 in 2-ol? So you are given this alpha beta unsaturated ketone here, and four reagents are given to you. You have to choose which one of these four reagents will predominantly give you the carbonyl addition rather than the 1,4 addition. Okay, you have to choose the reagent which will give you the 1,2 addition here on the carbonyl. So let us go through the reagents one by one. To solve this question, if you remember, Professor Harinath Chakrapani sir has taught in his video lecture about hard soft nucleophiles. Okay, that hard soft nucleophile video will help you in solving this lecture. But to summarize that video, here is a list of hard and soft and also borderline nucleophiles. When it comes to 1,2 addition on carbonyls, this particular electrophilic center is hard electrophile, and for 1,4 addition, this particular carbon center, which is electrophilic, it is actually softer. Okay, so yes, yes. Does anybody have any queries regarding this? Otherwise, I would suggest you all to keep your mics muted so that uh, the incoming voice doesn't disturb the other students. And after knowing the concept of hard soft electrophilic centers in this alpha beta unsaturated ketone, you must know that hard nucleophiles will get added to the hard electrophilic center, and also the soft nucleophiles will get added to the soft electrophilic centers. And following this particular concept, out of these all four reagents, you will know that A, B, and D, all of these three are going to be added to the 1-2 addition fashion. Okay, except C, all three reagents are going to add in 1-2 addition fashion. But you have to choose the most reactive one out of these three. So here is the explanation for this particular question. Organolithium reagents are more reactive towards carbonyl addition product than Grignard. Of course, Grignard reagents are also going to give you predominantly the carbonyl addition, but they will also give you some amount of the conjugate addition product. So for this question, you have to choose option B, which will give you large fraction of the carbonyl addition product. So this phenyl lithium organolithium reagent will be the correct answer for this question. So this list will be very important while solving these type of question. You may note down or take a screenshot of this. And after this, let us move to the next question. This is also similar question on the same concept. Which of the following predominantly gives the conjugate addition product with pen 3 into one? The same substrate you have now, and out of these four reagents, you are asked which one of these four will predominantly give you the 1,4 addition product. Like the incoming nucleophile will add up here and the reaction will go ahead. So like we have already discussed, right, in the last question, out of these four reagents, option C is going to give you the product in which you will observe 1,4 addition of the phenyl nucleophile. So if we talk about organocuprate reagents, this is how they are synthesized by reacting organolithium reagents with copper iodide, and these uh, these nucleophiles in this organocuprate reagents act as comparatively soft nucleophiles when it comes to uh, organolithium or Grignard reagents. These are softer nucleophiles. Okay, this is why they prefer to get added to the soft electrophilic center rather than this hard carbonyl carbon. Okay, so always remember organocuprates will give you 1,4 addition product. So out of these four reagents, for this question you have to choose option C as the correct answer. So after this easy question, let us move to the next question. Which is the main final product of the following reaction? You have this beta ketoester substrate, and we are treating it with this alpha beta unsaturated ketone, and two steps are involved in the reaction. In the first step, we are treating these two substrates in presence of sodium ethoxide base in ethanol solvent. That means proton source is present there, and in the subsequent step, we are treating the whatever product you will get in step 1, we are treating it with acid, aqueous acid, and we are also heating the reaction medium. Okay, so in the first step you will get an intermediate product, and then with treatment of acid you will get a product which will undergo some chemical conversion upon heating in the second step itself. Okay, these points you have to identify before approaching the question. So let us discuss this reaction mechanism step by step, how it will follow, and similar reaction mechanism we have already discussed in last two tutorials where we studied condensation reactions. Okay, so let's start the reaction from this substrate. First of all, we have base. So this will abstract the acidic proton from this substrate. Okay, so two types of acidic protons are present here. One is this way and the other is this way. And among between these two centers where acidic protons are present, since sodium ethoxide is a base which is going to give you the thermodynamic enolate, like we discussed in the tutorial for enols and enolate. So in this case, to get the thermodynamic enolate, you have to abstract the proton from this center, isn't it? So after abstracting the proton from this center, you will get an enolate which will be in conjugation with this carbonyl CO bond. Okay, so that enolate is going to come back to attack at this alpha beta unsaturated ketone, and thereby you will get a product which is similar to option A, but in this hydroxyl group, in the first step you will have OET. Okay, because this OET is written here in this fashion. Just imagine CO and OET here, and after attacking at this substrate, this long chain is going to be installed in the substrate now. Okay, so the first step product will be, you can consider option A, where OH will be in OET form. Okay, that will be your first step product. So after achieving at that product, we are treating it with aqueous acid. So now if you have an ester in the product, like I said, you have COET here. So that ester group will get hydrolyzed by the acid. Okay, so after hydrolysis, now you will achieve at option A. Okay, till now you are at the option A product, but you cannot choose option A as the right product. Why is it so? Because we are not stopping the reaction at this acidic stage. We are also heating at the end. Okay, and what happens when we heat beta keto acids? I hope you remember from the last tutorial, beta keto acids undergo decarboxylation easily. They remove a carbon dioxide molecule from the structure when we heat them. Okay, and you can revise the last tutorial's concept, the decarboxylation concept, from this particular slide. What happens when you heat the beta keto acids? They can undergo a transition state which is similar to this structure written here, and they can easily undergo decarboxylation to give you an enol of this form. But it doesn't stop at this enol form, of course. It will undergo ketoenol tautomerism to give you ketone. And if you notice it closely, you can just say this mechanism as this COOH carboxylic functionality of this beta keto ester is simply replaced by one hydrogen. Okay, at the end of this decarboxylation, like you are just removing the carbon dioxide molecule from the carboxylic acid functionality. So what remains there? This is a hydrogen, a proton. So it just gets attached to the carbon from where you are removing the carboxylic functionality. That is the result of decarboxylation. So since after acid hydrolysis of the product, we are heating it, so you have to remove carbon dioxide from this option A product. Okay, and what we observed, simply carbon dioxide goes from here, and this particular proton, you can imagine that it is getting attached to this place from where carboxylic functionality is leaving. So ultimately you are going to get option B as your final main product. Okay. So this is the description. Hydrolysis of the ester and decarboxylation of the beta ketocarboxylic acid, which is happening in the step 2, is giving you this final product in option B. Okay, so do not get confused. Do not just stop at the option A, because we are also heating. If this thermal sign was not there in the question, you have to choose option A as the correct answer. But and also you must remember beta keto acids are very feasible for decarboxylation. Okay, otherwise it would not go for further reaction, and you would have gotten only the acidic product. Just because of the presence of this keto functionality in the beta position, this carboxylic acid group is decomposing and leaving a carbon dioxide molecule. So I hope this is clear, and you can note down the description. If you have understood the concept, you are good to go. So let us move to the next question. This is also a very interesting question on reaction mechanism. Which is the main product of the following reaction? You have a diketone given here and another alpha beta unsaturated ketone here, and similar reaction conditions are kept. You have sodium ethoxide base in ethanol solvent. You have proton source present in the medium. So how this reaction is going to proceed? What did we do in the first step? We abstracted the acidic proton from the first substrate. This reaction is actually undergoing and following Robinson annulation mechanism. Let us look how this reaction proceeds. First of all, in the question you are given sodium ethoxide. You just imagine it as a base. So base will abstract the most acidic proton from the substrate. So here you have two possibilities in this symmetric molecule. Either you can abstract proton from here or here, but you are given thermodynamic enolate giving base sodium ethoxide, so you have to choose the enolate which will be present with highest number of substituents. So that highly substituted enolate will be observed when you will abstract this particular proton. Okay, so after abstracting this proton, you will get this carbon ion first, which is of course stabilized as an enolate, and that enolate will now get added up to this alpha beta unsaturated ketone. Okay, so this conjugate addition will give you this second enolate which is generated. Okay, and since you have proton source in the medium, quickly this oxyanion will get protonated to give you enol first, and after tautomerism you will get this triketone fragment now. Okay, but is this option given in the question? No, right? That means you have to proceed further for getting the correct answer. Okay, otherwise we would have chosen this as a correct answer. So to proceed further, again the base will now abstract the most acidic proton. So to talk about most acidic proton now, you have a ketone here. Okay, and both the sides in the from both the sides you can abstract proton and attack at the carbonyls in this symmetric structure. But if you abstract proton from this particular carbon, after attacking at the ketone groups, you will get a 4-membered ring. I hope you are uh, getting to understand what I'm trying to say. If you abstract proton from this particular position, you will get an anion which is going to attack at the carbonyl and to give you 1, 2, 3 and 4. 4-membered ring which will be highly sterically hindered. So you have to choose this other side carbon for abstraction of proton. Okay, so after choosing the carbon, you have to abstract a proton from here by the base to get this second carbon ion in the reaction. Now this carbon ion can easily attack at either this ketone or this ketone, doesn't matter, the product will be same, है ना, because this is symmetric. So let us consider that it is attacking at this carbonyl, and after attacking at this carbonyl, you can show the arrow pushing towards this carbonyl oxygen to get a negative charge at this oxygen atom. Okay, now it will easily get protonated by taking proton from the protons rich medium, which is ethanol we are taking as a solvent. So after protonation you are getting this diketone compound. Okay, again this compound now will undergo an E1CB mechanism reaction, and thereby you will get a product which will be similar to this. Okay, first if you imagine it as a dehydration reaction, first you will get a double bond here. Okay, but it will quickly get isomerized to give you this more stable alpha beta unsaturated ketone. Why is this more stable compared to the double bond here? Because this double bond will be in conjugation with the ketone. Okay, that is why these, in this particular question you will get this alpha beta unsaturated ketone as the major product, and thus by Robinson annulation mechanism in this reaction you will get option B, not B, option C as the correct answer. Okay, I hope this is clear. It is just option C product, the orientation is reversed. Yes. Yeah, option C is the correct answer. So the mechanisms are interlinked and they are quite similar. You just have to first choose the acidic proton and then you will attack at the electrophilic center to get enolates, and if you have proton source you will protonate the oxyanion formed. If you do not have proton source and you have a leaving group attached at the carbon, you have to eliminate that leaving group from the product. Okay, we will come across those kind of examples as well. So after this Robinson annulation related question, let us move to the next question of this tutorial. Which of the following does not undergo a conjugate addition reaction with butanamine? Okay, so you are given 4 types of substrates and butanamine nucleophile you have. Okay, you have an amine nucleophile which is basically a borderline nucleophile. It can undergo 1,2 also and 1,4 also. So out of all these 4 substrates, which one will not undergo conjugate addition, like in which one substrate butanamide will not add in 1,4 fashion. Let us see. To get aided in 1,4 fashion, the double bond of alpha beta unsaturated ketone or maybe alpha beta unsaturated ester, that double bond must be electron deficient. Why is it so? Because in conjugate addition, we are adding the nucleophile at the fourth position, right? Fourth with respect to the oxygen. So we are adding it in the fourth position. So if nucleophile, which will be electron rich, okay? If nucleophile has to be added at the fourth position, this position has to be electron deficient. Otherwise, if it is electron rich center, the incoming electron source is going to experience electronic repulsion. That is why this fourth center must be electron deficient. Now, let us screen all these four substrates and choose the one where this particular fourth position is not electron deficient. Let us look at the substrates. Consider option A. In this one, it is a ketone and the double bonded electron pair will be pulled by the carbonyl carbon oxygen double bond. Okay, this double bond you can shift here, and this carbon oxygen double bond you can show arrow pushing towards more electronegative oxygen. So you will get an enolate with O minus here and the double bond will be here, and thus this particular fourth position is electron deficient because of electron pulling via carbon oxygen double bond. So option A will give you conjugate addition. There is no issue here, right? And then comes option B. It is actually a little more electron rich center as compared to option A. If we talk about this carbonyl carbon, because it is already getting electrons from this methoxy substituent as well, but it will not hamper the conjugate addition because even after the presence of OMe here, still ester functionality remains as containing electrophilic center at this carbon. So this carbon oxygen double bond also will pull the electron pairs from this carbon carbon double bond. So in this substrate also, this center, the fourth center, will give you conjugate addition because it is, although it is less electron deficient than option A, but it will also give you conjugate addition. So we are sorted with option A and B. These two are not our correct answer. Either option C or D will be our answer. Okay. So out of these two, if we see in option C, what are we seeing? We have this double bond adjacent to oxygen atom, okay, which is containing two lone pair of electrons. And this particular oxygen atom can push its electron pairs not only towards the carbonyl but also towards the carbon carbon double bond. Okay, this oxygen can push its electron pairs towards both the sides of it, thereby making this carbon carbon double bond highly electron rich. Because imagine it is pushing the electron pairs towards this side, then you can show the arrow pushing like this way and you will get here C minus. Okay, if you imagine O positive after donating the electrons, you will get a C minus here. So it is an electron rich center. So if nucleophile approaches it to give you conjugate addition, it will hamper the reaction and it will repel the incoming nucleophile. So option C you can choose as the correct option, which is not going to give you conjugate addition. If it has to react with this carbonyl carbon, it has to undergo reaction in 1,2 fashion. And if we talk about option D, it is again a ketone only. Just it is containing an extended conjugation, but the electron pairs of these double bonds will anyway rush towards the carbon oxygen double bond. Okay, so here also 1,4 conjugate addition will be possible with butanamine. Thus, we chose the option in which the conjugate addition is not feasible due to the presence of electron-rich carbon-carbon double bond. So, this will be the brief description of the question, and you have to choose option C as the correct answer. So, with this, let us move to the next question. Which of the following does not selectively give the product of conjugate addition with ethyl butanoate? Again, you have a alpha beta unsaturated ester and you are given 4 types of reagents which are going to give you nucleophilic addition, and you have to choose that particular option which will not give you conjugate addition. Okay, is it sodium cyanide in water? Is it butyl lithium? Is it butylamine, or is it this thionucleophile? Okay, so again you have to take the help of the hearts of nucleophile list, and from that list we know that when it comes to organolithium compounds, it is always going to give you the carbonyl addition product rather than conjugate addition. Okay, for the other options, if you look at this particular list, cyanides and sulfur, being large in size, always prefer to get added to the soft electrophilic center. Okay, this option A and option D, they will predominantly give you conjugate addition, and option C, being a borderline nucleophilic reagent, will give you both 1,2 and conjugate addition. But when it comes to option B, it will give you major product where you will observe 1,2 addition. Okay, you will observe the butyl addition in only the carbonyl center. Very trace amount of 1,4 addition may be possible in this reagent, but major fraction of the product you will get carbonyl addition only. So thus you have to choose option B as the correct answer. Then let us move to the next question, which is also easy to whatever we have solved already in this condensation reaction topic. Which is the main product of the following intramolecular Claisen condensation? You have a diester substrate now, and 3 steps are involved in this reaction. In step 1, we are treating the substrate with sodium ethoxide in ethanol, and whatever the product we are going to get, to that product we are going to dump methyl iodide. Okay, and after the completion of the reaction at step 2, we are going to treat that product with base, and then lastly with acid under heating condition. So quite a long process. Let us go step by step what we are going to observe. So if we talk about acidic protons in this substrate, it is a symmetric molecule. You can either abstract the first proton from here or here. Okay, it doesn't matter. Both the sides are equivalent. You can abstract the proton from either side. So let us consider that we are abstracting the proton from this carbon. Okay. So after getting that carbon ion, which will be in conjugation with carbon oxygen double bond and it will give you enolate, and that enolate will come back to attach at this ester carbon. Okay, and now for this ester carbonyl you have a very good leaving group attached to this carbonyl. Okay, so rather than protonation of the oxyanion formed after attack, this ethoxide will leave. Okay, why? Because you have a very good leaving group attached. So this carbon you can connect to this carbonyl carbon and this ethoxide will move away. Thus, you will get a product which will be somewhat like this, and this methyl is coming after step 2 where we are adding the methyl iodide. Okay, I hope you got it. We abstracted the proton from here, attacked at this carbonyl, and due to the presence of ethoxide here, this ethoxide will move away and you will get this 5-member cycle. And if you abstract the second acidic proton from the same center, that carbon ion will attack methyl iodide, which we are going to add in the second step, and you will get this methylated ketoester. Okay, now in the third step, what did we do? We treated the ketoester of second step with sodium hydroxide base. So simply the product will undergo ester hydrolysis with sodium hydroxide and you will end up getting this beta keto acid. This beta keto acid is now treated with hydrochloric acid in presence of heating condition. Okay, what was the fourth step? It was HCl and heating condition. So this reaction will not stop at this beta keto acid step. It will now undergo what? It must be very easy for you now. It will undergo decarboxylation reaction. And you have to simply replace this carboxylic acid group by a proton attaching here. And you will get this cyclopentanone as the final product. Okay, the CH3 was already here, but this carboxylic acid group after decarboxylation will be replaced by one hydrogen which will be attached to this carbon. Okay, so this cyclopentanone product will be the final product for this question. So out of all these 4 options, you have to choose option D as the correct answer. I hope these mechanisms are being much easier for you now. And let us move to a very similar question. Which is the main product of the following intramolecular Claisen condensation? The substrate itself is a cyclic compound where you have a keto functionality and also an ester functionality. We are treating it with sodium ethoxide in ethanol, and in the second step we are adding the methyl bromide substrate. So out of ketone and ester, you must already know that the ketone carbonyl carbon is more electrophilic and the adjacent protons are more acidic in nature as compared to that in the ester. Okay, out of all these three protons, these two side protons will be more acidic. Why is it so? Because for ester, you have electron pushing from the ethoxide oxygen. Okay, so this center is not that much electron deficient, and thereby these two protons will not be that much acidic. But for the ketone, these two side protons will be acidic. Now you have two possibilities of abstraction of proton. How? One proton is here, present here, and three protons are present in the methyl. You can abstract protons from either here or here. And by looking at the type of base given to you, which is a thermodynamic enolate producing base, you may think that you are going to abstract the proton from here. But you have to look at the number of atoms that are going to be present in a newly formed ring. Like if you cyclize after abstracting the proton from here by attacking at this ester carbonyl, how many membered ring will you get? It is a highly sterically hindered 4-membered ring which is going to be formed. And whenever you have the possibility of forming 5 or 6-membered ring over 3 or 4-membered ring, you have to always follow the path where you are going to get stable 5 or 6-membered ring. So if you look at this methyl protons, if you abstract protons from here, you will get 1, 2, 3, 4, 5, 6. You are going to get 6-membered ring. Okay, but if you abstract proton from here, you are going to get a 4-membered ring. 1, 2, 3, 4. So you have to abstract the protons from methyl, and rather than getting the thermodynamic enolate, you are going to get the kinetic enolate in this exceptional example. So after abstracting the proton from here and after attacking at the ester carbonyl, you now have to give away this good leaving group attached. Okay, whenever you have a good leaving group attached at the electrophilic center, you have to just move it away. Okay, so now you can imagine this carbon will get attached here and this ethoxide will leave. Okay, and in the next step, what happens? You have methyl bromide. Okay, so the reaction is not stopping at the diketone form, and further abstraction of acidic proton will take place. Okay, and that acidic proton abstraction will give you the second carbon ion and thereby the second enolate, and that second enolate is going to attack at methyl bromide to give you this methyl attached at this carbon. So this product you are going to get as the final product of this intramolecular Claisen condensation. Uh, Maybe condensation you cannot call it, you have to call it Claisen reaction, because we are not removing the water molecule here. So at the end of this Claisen reaction, you have to choose this option as the correct answer. Okay, I hope the mechanism was clear to you and why we chose the kinetic enolate rather than thermodynamic enolate. That concept you must remember while solving this particular type of questions. You have to always forbid formation of 3 or 4 member cycles. Okay, if you have the possibility of 5 or 6 membered rings, always follow that path. So again, we have a question related to hard-soft nucleophile. Which of the following does not undergo an addition reaction with butanamine? You have 4 alkenes with 4 different substituents present, and out of these 4 alkenes, one will not undergo addition reaction with butanamine, which is nucleophile, and if you want to attack at this double bond by this incoming nucleophile, like I said, you need a electron deficient carbon carbon double bond. So you just have to see and choose that particular option where your carbon carbon double bond is electron rich and is containing electron donating group. And if you look at the substituents present here, you already know that this tertiary amine in the nitrogen, the lone pair of electrons, the electron rich nitrogen can push its electron pairs towards the carbon carbon double bond, and you can choose it as the electron donating group as compared to the other functionalities present in the question. Okay, cyanide in and nitro are highly electron withdrawing groups, and for aldehydes also, the electron deficient, that is electrophilic carbon oxygen double bond of the carbonyl, can pull the electron pairs of this carbon carbon double bond towards itself, thereby making this carbon center electron deficient. So in option A, B, C, you have electron deficient carbon center present at which the incoming nucleophile can attack. But in case of option D, you have a an electron rich carbon center present here as compared to the other 3 options. Okay, so you have to choose option D as the correct answer for this question. So lastly, we have 4 sets of reactions, and you have to choose one option from here which is not showing you the correct main product. Okay, 4 reactions are given. Which of the following reactions shows a wrong main product? So to choose the wrong main product, let us go through the reactions one by one, and we are going to discuss the mechanism that these reactions are going to follow. Okay, option A, we are treating this alpha beta unsaturated aldehyde with ethyl magnesium bromide. Firstly, in presence of ether solvent, and secondly, we are working it up with acidic water. Okay, second step is just work up. We are going to work it up with acidic water where the anions will get protonated in the second step. So first step is the main reaction here. So what will happen when you add this Grignard reagent to the alpha beta unsaturated aldehyde? You will get addition at this you will get addition to the 1,2 fashion predominantly, because like we have already discussed, when you have organolithium and Grignard reagents, you are going to get 1,2 addition predominantly, and then some fraction of 1,4 addition will be formed, which will be of course much lesser than the 1,2 addition product. So this incoming ethyl should attack at this carbonyl to give you OH here. Okay, and the OH, firstly you will get O minus oxyanion, which will get protonated at the workup stage. So at the final product, you should have ethyl attached to this carbon and OH here. You can say alpha beta unsaturated alcohol should be the major product for this reaction. But in the option, you are given that the incoming ethyl nucleophile is attaching in 1,4 fashion, and the aldehyde substituent is staying intact, which is not matching with the hard, soft concept. So we can say that option A is not showing you the correct main product. I hope you understood. Okay, you may go through the list of hard soft nucleophiles again, and you will see that for this particular question, the major product should be alpha beta unsaturated alcohol. So we will keep in mind that option A is not showing the correct main product. Again, let us go through all the remaining three options. In option B, what is happening? You are given a secondary amine and you have this alpha beta unsaturated nitro compound, and we are treating it together in presence of ethanol solvent. Okay, so you have this electron deficient carbon carbon double bond, and these kind of substrates we discussed in Henry reaction. Okay, but it is a little different from Henry reaction, but the substrate is same. This nitro substrate is same. So this incoming nucleophile will add up to this double bond at this electron deficient center, which is in conjugation with the electron withdrawing nitro substituent. And you will generate a carbon ion here, which will take up a proton from the ethanol solvent present in the medium. Okay, so the incoming secondary base you have to attach here, and the carbon ion generated after arrow pushing will be protonated at the center, and you will get this product as a final product. I hope this was clear. What we did, this amine we attached here, and after attachment of Et to N here, you already have CH2 here, and protonation will give you another CH2 here, and this NO2 substituent will remain intact, and you will get this product as the final compound. So option B is showing you the correct main product in the question. Now let us come to option C. You have this tertiary amine here, which is alpha beta unsaturated again, and you have this cyano substrate, again alpha beta unsaturated. In presence of ethanol solvent, we are treating it first, and then we are working it up with sulfuric acid and water. So let us focus on the first step first. In the first step, what happens? This nitrogen is going to push its electron pair towards this carbon nitrogen single bond, and thereby this carbon carbon double bond will get attached. It will get aided up at this electron deficient carbon center. Okay, and after this addition, what will you get? Positive charge will get generated here because we are giving up its electron pairs. So nitrogen will attain a positive charge here, and you will get carbon nitrogen double bond here, and this double bond will become single bond now, and this carbon will get attached to this carbon. Okay, that product you will get. And the second step is basically whatever iminium ion we generated here, carbon nitrogen double bond with positive charge on the nitrogen, that iminium ion is hydrolyzed in the second step. Okay, that iminium hydrolysis will give you addition of water molecule at this center, and this secondary amine will leave out. Okay, this amine functionality will leave by breaking of this carbon nitrogen bond, and water molecule will add up here. Thus, after ketoenol tautomerism, this product you will get as the final product here. Okay, in the first step we showed the addition of this substrate to the cyano substrate by pushing electron pairs from nitrogen, and then this double bond got added to the conjugate addition. And second step is going to hydrolyze the iminium after pushing the electrons from nitrogen. Whatever iminium we got, that iminium is going to be hydrolyzed in presence of sulfuric acid in water medium. So option C is also showing you the correct main product. Now we are left with option D, where we are treating this diketone compound with alpha beta unsaturated ketone in presence of sodium ethoxide base and ethanol solvent. So we have already discussed one question which was very similar to this, just the second substrate was a bit different there, but the reaction was following Robinson annulation. What happened? First, the sodium ethoxide base abstracted the acidic proton which is present between the two ketones, because this is going to give you the thermodynamic enolate, and that enolate is going to attack at the alpha beta unsaturated ketone in conjugate addition fashion. And after the conjugate addition, you are going to get the second enolate of the reaction. This second enolate is first going to get protonated by the help of the ethanol solvent present, and after the protonation, the reaction will further proceed by now abstracting the acidic proton from here. And this abstraction will lead to the second attack at this carbonyl. And like I said, both of these carbonyls, any one of these two carbonyls you can attack with this carbon ion or enolate, you can say, because this is a symmetric part. Okay, both these two carbonyls are equivalent. So after the attack at this carbonyl carbon, we are cyclizing this second fragment and we are getting the third oxyanion. Okay, this third oxyanion is again going to get protonated, which upon subsequent dehydration is going to give you the desired product, which is this product. Of course, this six-membered ring is not drawn properly, but this product you are going to get, which is exactly the same as this product here. Okay, after hydrolysis, you are going to get this alpha beta unsaturated ketone formed here, and this diketone product you are going to get as final product for the question. So option D is also showing you the correct main product. So after the four options, after analyzing all the options one by one, we got that only option A is the one which is not showing you the correct main product. Okay, in this particular reaction, you should have gotten alpha beta unsaturated, not alpha beta unsaturated, you should have gotten the addition of ethyl to the aldehyde. Okay, yes, and the double bond should have been intact, and in this particular place you should have gotten an alcoholic substituent. Thus we have solved the question. Let us move to the next, a little longer question, but again, whatever mechanisms we have already discussed. By now, you may are feeling that yes, you are feeling confident while solving these mechanisms, and that is the purpose of solving all these mechanisms thoroughly. Let us solve this reaction sequence, which is a longer reaction sequence. What will happen if we treat this cyclic ester with methyl magnesium bromide in presence of water to get product X first, and then in the subsequent step we are going to treat product X with sodium ethoxide in ethanol. Okay, so you have to identify what is the compound Y. Okay, so you have, if you look at the kind of substrates and reagents, you have this incoming nucleophile present in the reaction medium where it will be methyl, and you have to attack at the electrophilic center, which will be this ester carbonyl here, isn't it? So you can start approaching the question by attacking this carbonyl via methyl, but you must look at the substrate that here you cannot immediately protonate the oxyanion that is going to be formed because you have a leaving group here. Okay, always we have whenever you have ethoxy methoxy, we are going to proceed by giving up the leaving group. So this is the leaving group here, so we are again not going to protonate the oxyanion. We are going to move away the leaving group present here. So to approach this question, like I said, we are going to attack at the ester carbonyl first, and the oxyanion will push up its electron pairs to give away the leaving group, and again the leaving group is in conjugation with carbon-carbon double bond. Okay, so you can show the arrow pushing in this way, and you will get a new carbonyl formed by breaking the carbon oxygen double bond to give away the leaving group. Okay, so this first intermediate product will be formed. Again, the reaction will not stop at this stage. It will follow the mechanism of Robinson annulation. You have to abstract the acidic proton again, and as we have already discussed, for this intermediate product you have two possibilities of abstraction of proton. One is this side and the other is this side. Okay, so here if you abstract protons from this side, you will get a 4-membered ring formation. Okay, so we will preferably abstract protons from here, which is going to give us 6-membered ring cyclization. And after abstracting the proton from this methyl, you will get, of course, the kinetic enolate, which is going to get added up to the carbonyl present in the second ring. Okay, and you will get formation of this bicyclic compound with oxyanion here. This oxyanion gets protonated first, and then on the subsequent step it will undergo dehydration, or it will follow E1CB mechanism to give you this alpha beta unsaturated Robinson annulation product as the final product. Okay, if you understand the concepts of abstraction of acidic proton and attacking at the most electrophilic center, and also if you look closely at the type of ring that can be formed by the attack of enolate at the electrophilic center, you are good to go while solving this mechanistic problems. Okay, so this is again an example of Robinson annihilation reaction. So with this we have more or less covered a lot of questions on the topics conjugate addition versus carbonyl addition, and also we have discussed a few more higher level questions on the topic of condensation reactions. Okay, so let us recap whatever we have discussed. We first started today's tutorial with this question where we went through the list of hard and soft nucleophiles, and you can if you find difficulty in this hard soft concept, you can again go through the video lecture provided by Harinath Chakrapani sir. He has very nicely explained this concept of hard soft nucleophile. So by going through that concept, we chose that organolithium compounds predominantly give 1,2 addition product. Okay, and in the next question, similar concept, organocuprates always will undergo 1,4 addition rather than 1,2 addition. Okay, we also discussed how these organocuprates are formed, and then we had this question from condensation topic, and we again revised the concept of decarboxylation of beta keto acid. Okay, and we saw that the reaction did not stop at the beta keto acid stage, rather it underwent decarboxylation to give you this diketone product. And then in the next question we discussed the mechanism of this Robinson annihilation reaction, and we saw what are the steps involved in this mechanism. Okay, and in the next question we discussed how to get a conjugate addition. You always need a carbon electron deficient carbon carbon double bond preferably. So we chose option C as the correct answer here, which will not undergo conjugate addition reaction with primary amine. And again, the next question is from the topic hard soft nucleophiles, and we discussed that again organolithium compound will not give you conjugate addition, rather it will give you carbonyl addition product. So next we had this example of intramolecular Claisen condensation, and we observed the formation of cyclopentanone, and this reaction again involved decarboxylation as the at the last step. So next, another intramolecular Claisen condensation we went through, and here we discussed whenever you have the possibility of 3 or 4 membered ring formation versus 5 or 6 membered ring formation, you have to always choose the second category. Even if you have to get kinetic enolate in presence of thermodynamic enolate producing base, you always have to form the sterically more stable ring. And thus we got this product where we formed 6 membered ring in the second cyclization. Okay, and then we again came to the concept of hard hard soft soft, and the alpha beta unsaturated carbon carbon double bond here in the option D was not sufficiently electron deficient, so it did not undergo addition product with primary amine. Then we discussed this set of questions where we saw that except option A, all the 3 options was listing the correct main product. We also briefly discussed the mechanisms involved in all these reactions, and we chose the first option as the wrong main product, because Grignard reagents should give you 1,2 addition products as the major product. Okay, and lastly, we discussed this question where we observed involvement of Robinson annulation reaction mechanism. When we went through step by step, this intermediate product underwent Robinson annulation to give you a six-membered ring in the second cyclization rather than four-membered ring. Okay, so with this we have discussed all the questions of this seventh tutorial for the course. So you can go through the video lectures which were very interesting this week, and if you have any queries you can feel free to ask. Thank you everyone for joining for today's tutorial.